Hello friends, I am Nikita and you are watching Prepare for Tea. Today, the content of our discussion will be on filters and oscillators. We will be discussing active filters, sinusoidal filters, criteria for oscillations, wave shaping, 555 timer. Moving with the active filters, filters are analog devices which filter out particular band of frequency or passes specific set of frequency according to their characteristic traits. Usually, transfer function helps in knowing the characteristic of a filter. Our transfer function is a mathematical form where the numerator defines the set of zeros and denominator the set of poles. Often the pole can be either real or complex conjugate. Here I would like to show you that we have an S-plane. In S-plane, this is sigma and this is j omega. Mostly, it is likely to be considered that all the poles should lie on the left hand side of the j omega axis, making the whole, or on the real axis, making the system stable. This could be there could be the first order or second order filter. Few filters that we listed below are low pass, high pass, band stop, and all pass. Earlier we have discussed that an integrator is a low pass filter. It passes all the low frequency and stops all the high frequencies. A differentiator is a high pass filter. So basically we are applying our amplifier calculations of integrator and differentiator in finding the low pass and the high pass filter and other filter. Let's look further what are the different characteristics or transfer function of these filters. Now the low pass filter. Low pass filter, first order and second order filter. The first order filter has one pole. This is one pole. Okay. It is a quadratic equation. The second order means it has a quadratic equation. It has two poles. The high pass filter not only has one pole but has also one zero at zero. The high pass filter has two poles and two zeros. Here the zeros will be on input. Now the all pass filter. The all pass filter has a real zero and a pole. Similarly, the second order has two real zeros and two poles. For the band pass filter, the first order doesn't exist because it has to have two frequencies, a high frequency and a low frequency, because it is almost like a band. It should have H and F of L, right? To make it show it characteristic, that is the band pass. So the tune amplifier are LC amplifier. What are LC amplifier? LC amplifier are those amplifiers which have a inductor and capacitor in parallel. Okay, for that the omega naught is 1 over root LC. They have a 3 dB bandwidth by 1 over RC. Q factor is omega naught over B, which is equals to omega naught RC. Is this, or it could be in parallel to omega naught over omega I is equals to minus G into R. Now let's look at IC 555 primer. IC 555 primer is it acts as a multi-vibrator, monostable multi-vibrator, or bistable multi-vibrator, or stable multi-vibrator. What are these three terms? We will get to know shortly. But for astable multi-vibrator are those vibrators which have a capacitor and a resistor, and which shows a frequency and its period of oscillation increases and decreases with time. Sorry for the diagram, but this is time, and they show such pattern because you can say that when t is low, then most of the time the capacitor is discharging. By this, the capacitor is discharging to the ground, and it will show T low. Okay. And for T high, it will be charging with RA, RB, and C short circuited. Okay. So this will be the formula. Now total T will be equals to 0.69 RB plus 2 RA, and frequency is equals to 1.44 or divided by C RB plus 2 RA. Now let's look at one of the 2016 question which was asked to calculate the frequency of oscillation. We have just discussed the formula that it is 1.44 divided by C RA plus RB plus 2 RA. Okay, put that formula and you get the frequency. Some questions in the GATE examination are very simple, very straightforward because they are 1 markers. And 1 marker numerical questions are sometimes straightforward. You have to apply just the formula. The monostable multivibrator. The monostable multivibrator is stage 1, and it changes its state only when a trigger is hit and return back when trigger is released. T high is 1 point RA/RC. It could be just like a trigger for this particular time T. It was high. That could be a monostable vibrator. Now let's look one of the 2015 question. The topic of hysteresis I haven't included, but I wish you to include that too when you are studying. So bam, this was a 2015 question. They asked about and they have given the hysteresis width, and they want to know the value of R. As Vin is connected to the positive terminal of the battery, then VTH is Vset R1 by R2, and VTL is minus Vset R1 by R2. Hysteresis is VTH minus VTL. This will add up both the equations, and on solving we get R1 equals to 1 kilo. We have talked about filters a little bit. We have talked about IC555 timers. Now let's look about oscillators. Oscillators are very important part of op-amp application system. Now op-amp works in various multiple application, but this application is specific because in this the feedback is a positive feedback. It is a positive feedback back to the inverting terminal. That is E N equals to A upon 1 minus E. Okay, and for periodic oscillation we keep in mind that it follows this equation that A beta equals to 1. That's known as the Barkhausen criteria. So we can calculate the gain. If we know the beta. Okay, the gain can be easily calculated, which is equals to 1 over beta. Now the phase oscillation loop gain must be greater than 1, and the phase feedback network is 180 degree, which for each RC network it has a 60 degree phase shift. The frequency of oscillation is 1 over 2 pi RC root 6. Now the Wien bridge. The distinction of this oscillation from the rest of the oscillator is RC series component in the feedback and RC parallel component attached with the input. F0 is 1 over 2 pi root R1 C1 R2 C2. For the Colpitts oscillator, I remember Colpitts and Hartley by this form that I always got confused in remembering these things. So what technique I resolved is Colpitts starts with C and capacitor starts with C. So Colpitts have two capacitor CC, 2C. Okay, in that way I remember the Colpitts oscillator, and Hartley is opposite of that. To get the gain, if you wish to know the gain, the beta or this value is C1 over C2. The beta of this oscillator is C1 over C2, and for this it might be L1. Check for this Hartley oscillator. Okay. The next is again, just by looking at the diagram, you can say it's a Wien bridge. Parallel RC, series RC in feedback. So let's see the solution. The solution is, we know omega naught is 1 over RC. RC equivalent is 2RC, so frequency of oscillation is 1 over 2RC. Using Markusian criteria, we calculate Z1, Z2, beta is Z2 over Z1 plus Z2. Calculate this. On solving, we get beta equals to 1 by 5. Then A becomes 1 by 5. From a non-inverting formula, we know A is equals to 1 plus R2 by R1. And putting this formula, we get R2 equals to 4R. So that was all for today. I know it's a small lecture video, but most of the time the questions asked are also not that typical. You can go through this basic concept and practice more questions on it. Thank you. Have a nice day. Don't forget to subscribe to the channel for more video updates.